When we think about weather, we naturally picture the standard Earth system: water evaporating, forming vapor clouds, and raining back down. Because it is all we know, we tend to project our local neighborhood onto the rest of the galaxy. We expect alien planets to fall into recognizable categories, like rocky spheres similar to Mars, or striped gas giants like Jupiter. Our local solar system is a narrow blueprint for a universe that operates on far more extreme chemical rules. The James Webb Space Telescope gives us the engineering power to look past those local assumptions. It recently spotted an exoplanet that defies visual and chemical expectations. It glows a vibrant, hot pink. And the weather systems on this world do not feature water vapor. The clouds are made of literal salt. How exactly do the mechanics of thermodynamics forge a pink world with salt in the sky? We cannot take traditional, direct photographs of exoplanets because they are outshined by the intense glare of their host stars. To bypass the blur of Earth's atmosphere and look deep enough to solve this, we launched a telescope 1,000,000 miles into space. This animation demonstrates a process called infrared spectroscopy. The telescope catches starlight as it filters through the extreme edges of the exoplanet's atmosphere. Specific chemicals in that atmosphere absorb certain wavelengths of light. This leaves readable gaps, chemical fingerprints, in the incoming data. When astronomers decoded the light passing through this specific pink world, those exact fingerprints matched the chemical signatures for heavy salts and silicates. We are now tracking worlds that are chemically dynamic and violent. Which brings us to the most obvious visual question: why does the data indicate the planet is pink? The color signifies a planet in its infancy. It is an incredibly hot world, still glowing from the violent heat of its own creation. The specific atmospheric particulates surrounding the planet scatter that inherent thermal radiation. Instead of a standard red or orange glow, the scattered light produces a fierce magenta hue. In deep space, color serves as a direct thermal thermometer, revealing exactly how much internal energy a young planet retains. On Earth, mild temperatures allow water to evaporate and form rain. The hellish heat of this exoplanet drives a much heavier cycle. Down near the surface, the heat is so intense that heavy minerals, silicates, and salts actually vaporize straight into glowing gas. Looking at this atmospheric cross-section, we see these vaporized minerals riding massive convection currents into the slightly cooler upper atmosphere. Because that upper layer is cooler, the mineral gas condenses. Instead of liquid droplets, it forms solid, crystalline salt clouds. It is a fully functioning weather cycle, where the forecast consists of vaporized rock and suspended mineral crystals. Capturing this level of atmospheric detail relies entirely on the massive precision engineering of the Webb telescope. For decades, studying exoplanets meant watching for a tiny dip in a star's brightness, a simple confirmation that a planet existed. Now, we are mapping the specific chemical composition and daily weather reports of planets located trillions of miles away. This pink, salt-clouded world proves our quiet solar system is one unique sample of the galaxy, rather than a universal standard. The laws of chemistry remain universal, but in deep space, they create environments that look nothing like our own. The next time you look up at a watery rain cloud here on Earth, take a moment to reconsider what else is floating in the skies above. Right now, across the galaxy, there are swirling silicates, molten rain, and entire atmospheres thick with suspended salts. The universe is vast, violently hostile, and breathtakingly vibrant.